So thanks for the introduction. Yesterday morning, Roderick van Ees already told you to some extent about the NXE 3400 scanner from ASML. And today I will tell you more about the new optics which lies at the heart of this latest generation of EUV scanners. So the next 20 minutes will be about resolution, since there are three major highlights about this new optics, and that are its superior resolution of only 30 nanometers single shot, its maximized flexibility when it comes to pupil design, often without losing any throughput, and of course, its readiness for a high volume production. So just to remind you why resolution is important, Moore's law has driven the industry for quite some time now, and following this path directly translates into requirements for the optical system in a scanner. And it is Abbe's basic equation which relates the critical dimension, that is basically the resolution, for a given wavelength lambda, say EUV, to the numerical aperture of an optics and a process-dependent factor K1. And it is these two parameters which allow us to improve the resolution or to increase the resolution in every new generation of EUV optics. In fact, the EUV program has quite a tradition at Carl Zeiss for more than 20 years now, starting with the shipment of the first prototype and the small series with an NA of 0.25 in the early years of the centuries. We have now arrived at the third generation of EUV optics, that is the third generation of the NA 0.33 platform, I should say, and that is the Starlith 3400. Shipment has begun last year, and this platform targets the high volume production of EUV. And we are also already working at the next phase of EUV systems, having an even higher NA, and you can learn more about the latest news there in the talk tomorrow morning by Jan van Schoot from ASML. I will be focusing today on the NA 0.33 platform. So this is its optical column in a nutshell. It has two basic components, the illuminator and the projection optics. The illuminator has the task to transport the light from the source to the mask while shaping the illumination profile. And in the 3400, we have introduced a new design which allows to reduce the pupil fill ratio from 40% down to 20% without light loss and enhancing sigma to its optimal value of 1. Now really using the full NA of the system. And it is these two basic parameters which allow us to push the resolution limit down to 30 nanometers. And in addition, the design is more flexible. And I will tell you more about the benefits for customer application there in a minute. The projection optics on the other side demagnifies the image from the mask onto the waver. And here we rely on the proven 3300 optical design. However, we have managed to improve overlay and wavefront performance yet again to also support this increased resolution. So these two components basically define the outline of my talk. First, I will tell you more about the illuminator and highlight some of its new features. Then I will tell you about the latest performance of the projection optics. And at the end, I will tell you how we at Zeiss have prepared for the high volume production of EUV. So let's start with the illuminator. What you see here is a principal sketch of its functionality. The light coming from the source is reflected at the field facet mirror, which is basically a switchable fly's eye, onto the pupil facet mirror, and from there onto the mask. And the individual field facets can target different pupil facets, and in this process shape the illumination pupil. In the 3300 illuminator, one field facet can address two different pupil facets, and in this way provide some standard pupil supporting 16 nanometer half pitch. The 3400 design is more flexible, and here one field facet can address many different pupil channels, and this ultimately allows to support 30 nanometers resolution. So an increase of more than 20%. How do we come to this conclusion? Well, this becomes clear when you draw the pupil fill ratio, which is basically the fraction of the pupil filled with energy against the half pitch. And in this picture, the resolution limit is determined by the NA for an optimal illumination setting. And this is, in our case, the blue line here. The 3300, having a pupil field ratio, a minimal pupil field ratio of 40%, supports 16 nanometers half pitch and is thus located just on the right-hand side of the line, where imaging is still good. And when you cross the line to the other side, to the left side, your contrast loss becomes critical. So by increasing sigma then to its optimal value of 1, we approach this optimal line, and when we now decrease the pupil field ratio, we walk down that line and reach the 30 nanometer half pitch resolution limit for the 3400, which translates in a K1 factor of 0.32. And for subcritical features, there's also a benefit in terms of enhanced contrast. However, this superior resolution is not only on paper, but is already demonstrated by RSML. What you see here are ATP qualifications of 6 different 3400 systems for 30 nanometers dense lines, and the colors refer to different focal positions. And what you see is an excellent imaging performance with a CDU of 0.3 nanometers at best focus. And the process window is also pretty good. However, pushing the resolution limit is not the only new feature of the illuminator. The design is also more flexible and thus can provide a wide variety of different pupil designs. Next to the extreme dipoles, which are optimal for the ultimate resolution, it supports, for example, pupils from SMO, like this one here, for logic cut masks. And in case you're wondering, the optimization here can be done in such a way that the pixelization of the EUV pupil doesn't influence the process window. So the difference between the target shape, the blue area, and the red dots, which is the EUV pupil, doesn't matter. And the same is true for the illuminator efficiency, so there's no light loss with respect to the dipole. Moreover, there's no boundary condition on symmetry. So asymmetric pupils, like this one here, for example, can help to compensate for 3D mask effects and ultimately suppress unwanted telecentricity effects. And it doesn't end there. You can also think about more exotic pupil designs, and the next one is a rather, let's say, extreme example. Perhaps some of you still remember the old 1980s arcade game Space Invaders. For me, being born in 1980, this is actually more of a cultural memory thing. However, one of our engineers decided to highlight the flexibility of the new illuminator by imitating the shapes of the prominent opponents you are confronted with throughout the course of this game. And looking at these pictures, I'd say, he succeeded pretty well. However, the imaging application for these kind of pupils is, of course, still an open issue. So much for the potential of the new illuminator. However, this is not only theory and marketing, but the actual hardware is leaving our factory as we speak. Already 12 systems have been fully EUV qualified and meet all specifications. And our in-house qualification process includes a functional check of a couple of standard illumination pupils. And you can see one example here on the screen. I hope it's clearly visible. This is actual measurement data with UV light. So every pixel you see here on the screen is a pixel of some CCD camera. And you can see that all pupil channels are working properly, forming, for example, the large angular setting or extreme dipoles or quadrupoles optimal for 80 nanometer contact holes. Of course, this is only a single field point, but the intensity profile is pretty uniform over the illumination slit, having an uncorrectable uniformity of only 0.1% for the complete population. So to wrap up the first part, I think I have shown you how the illuminator extends the EUV family to 30 nanometers resolution while it maximizes your flexibility when it comes to pupil design. And then the next part, I will show you how the projection optics also supports this increased resolution. So, I've mentioned earlier, the optical design basically stays untouched. However, designing an optical system and building it are two different things. And so we have managed to improve wavefront and overlay performance yet again at this point. So we achieve this by constantly improving our production techniques to optimize the mirror surfaces. And after a first aspherization step, the mirror enter a closed loop production between ion beam figuring with a precision on the atomic level and a highly accurate interferometric metrology. And here we have reached a precision on the level of only a couple of picometers, actually. And by improving at both ends, we can control the surface roughness of the mirrors in every production step and ultimately reduce aberrations throughout the optics. And the result of this constant strive is an improvement in roughly a factor of 3 in the aberrations over the different generations of EUV optics. The 3400 shows a consistent wavefront performance with an RMS of just below 200 picometers, and distortion is also on an excellent level of 400 picometers throughout the population. And the tool-to-tool variation is also very weak. This is again data from our in-house qualification with EUV light. And this excellent performance is also already visible at waver level. Just last month, ASML recorded a record-breaking match machine overlay of just 1.2 nanometers using these machines. What you see here is the result of exposing individual wavers with two different 3400 scanners. And they all show a consistent performance with a match machine overlay of just below 1.2 nanometers. So also the wavefront performance translates into excellent imaging results. Yet again, I refer to ATP qualifications from ASML, this time for 60 nanometers isolated spaces. And you all surely know that this is a wavefront sensitive use case. And yet again, the CDU performance is around 0.3 nanometers at best focus for different orientations. The tool-to-tool variation, you can also think of it in terms of proximity bias with respect to the average population. And here, evaluation have been performed for different pitches and different orientations. And yet again, you see only a weak tool-to-tool variation with where you can recognize the consistent performance of the optics within. So, excellent imaging performance is one thing, productivity is another. And in EUV, transmission is a limiting factor there. And that is why we at ZEISS have been managed to improve the transmission of the optical column by a factor of 3 throughout the different generations. And the 3400 shows an impressively robust trend there, not only for the projection optics, but also for the illuminator with only a weak tool-to-tool variation. This is again data from our in-house qualification. So in conclusion, I'd say the projection optics is also ready to support 30 nanometers resolution with improved aberrations and overlay performance. So then let me use the last couple of minutes to show you how we at ZEISS have prepared for the high volume production and introduce you shortly or briefly to our factory site. Our production facilities are located just outside the city of Oberkochen in southern Germany, as many of you sure know. And you see here an overview of our factory. We have extended our production capacities to support the high volume production for the 3400 with additional buildings for optics, polishing, and for coding infrastructure, and also integration and adjustment has gotten additional space. And our R&D team stands ready to support production whenever help is needed. Speaking about R&D, we are also already working at the next phase, next generation of EUV optics. And here, anamorphic designs will allow us, or anamorphic designs with steeper spheres on bigger mirrors will allow us to increase the numerical aperture yet again to then 0.55, while the flexible illumination concept will basically stay the same. In terms of resolution, that means pushing the resolution limit by, yet again, by roughly 40% to then down to 8 nanometers half pitch, and in this way enabling Moore's law in the decade to come. However, this increase in resolution will mean bigger optics, and for bigger optics we will have to expand our production facilities yet again to prepare for the volume production of EUV. So here you see the additional buildings we are planning. And be aware that this is not only some plan on paper, but the actual construction is going on as we speak. What you see here is the shell of one of these buildings being raised these days, and this building is dedicated to our optics metrology. And by comparing it to the size, comparing it in size to the building in the background, you can get a first idea on the difference in size of the optics we are dealing here. So, coming to the conclusion, I've shown you how the Starlit 3400 optics pushes the resolution limit down to 30 nanometers by being a flexible low K1 imaging tool. And already 12 systems have been shipped to ASML and show an excellent imaging performance, and I hope I could convince you with my talk that ZEISS is fully committed to and ready for the high volume EUV ramp up we're all anticipating in the near future. So thank you for your attention.